Let's solve this problem, and as we do so, we'll pull out the general principles of what we're doing. So our first step is to bring all of the non-zero terms to the left-hand side. So bring all non-zero terms to one side. I'll take them to the left-hand side. So I'm actually adding 4x to both sides, so I have x squared plus 4x minus 5 less than or equal to 0. And now I have my quadratic. I've changed the problem to deciding whether some quantity is less than or equal to 0 or not. And my next step is to factor the left-hand side. And I'm looking for two numbers whose product is minus 5 and whose sum is 4. And so 5 and 1 should play a role, and the product should be minus, so 1 should be minus, 1 should be plus, and I need, when I add them, to get 4, so I should have plus 5 and minus 1. And I'm looking for the x values where that is less than or equal to 0. And the next step, recall, was to identify where the factors equal 0. And x plus 5 equals 0 if x equals minus 5, and x minus 1 equals 0 if x equals 1. And the next step, step 4, is to identify the intermediate subintervals. And remember, these are the subintervals where the sign of this product cannot change, because the sign of each factor changes only at one of these points where the factors are 0. So on these intermediate subintervals, the sign of the left-hand side of our inequality cannot change. Well, we can draw a number line, and our points of interest are x equals minus 5 and x equals 1. Those were the points where the factors may switch sign. And our intermediate subintervals, the first one runs from minus infinity to minus 5. The second one from minus 5 to 1. And the third from 1 to infinity. So these are our intervals. And now we check the sign of each factor. So we'll check the sign of x plus 5 on each subinterval, and the sign of x minus 1 on each subinterval, and this will tell us the sign of their product, x plus 5 times x minus 1 on each subinterval. So x plus 5 is going to be positive for x bigger than minus 5 and negative for x less than minus 5, and x minus 1 is going to be positive for x bigger than 1 and negative for x less than 1. And the sign of the product of these is going to be a minus times a minus. It's going to be a plus from minus infinity to minus 5. It's going to be a minus between minus 5 and 1. And it's going to be a plus times a plus between 1 and infinity. So we can say x plus 5 times x minus 1 is less than 0 on the interval from minus 5 to 1, and it equals 0 only if one of the factors equals 0, and that happens only at minus 5 and 1, so x minus 5 times x minus 1 is less than or equal to 0 if x is an element of the interval from -5 to 1, the closed interval. And that's our solution to our given inequality. Remember, the given inequality is equivalent to this one, and therefore the solution set to the given inequality is the same as the solution set to this one, which we figured out is the closed interval from -5 to 1. Now, there are two things that might come up or might have occurred to you as we've solved this, and that is, what if the quadratic in question does not split into two linear factors, two distinct linear factors? So remember, when we're given a quadratic, three things might happen. We might have two distinct linear factors, or we might have repeated linear factors, or we may have no factors. The quadratic may be irreducible, and all of this depends on the value of the discriminant, b squared minus 4ac. If that's positive, we have two distinct linear factors, or two distinct roots. If it equals 0, then we have repeated linear factors, or we have the same root repeated twice, and if it's less than 0, then we have no real solutions, or the quadratic is irreducible. It doesn't split into linear factors. And when we're solving inequalities involving quadratics that don't have distinct linear factors, in fact they're easier to deal with than the previous situation where we had distinct linear factors. The first situation is when we have a repeated factor and we have either x minus k squared, or a constant times x minus k squared on the left hand side, and we want to decide where it's positive and where it's negative. And the way to solve this is to keep in mind that x minus k squared is always positive. And so the set of numbers where x minus k squared is less than 0 is the empty set, and the set of numbers where x minus k squared is greater than or equal to 0 is all of the real numbers. And it's actually equal to 0 only when x equals k. So if we can rearrange our equation and there are repeated linear factors to our quadratic, then we're going to end up with a constant times this, and we're going to have to decide when that's positive and when it's negative. And keeping in mind that a square is always positive makes it pretty easy to solve. The other exceptional case might be that we have no real roots, and in this case we have an irreducible quadratic, and we want to decide whether where it's less than or equal to 0 and where it's greater than or equal to 0, or just less than 0 or greater than 0. Well, because this discriminant is less than 0, there are no roots, so there are no points at all where this thing equals 0. And remember, the graph of this, y equals ax squared plus bx plus c, can only cross from positive to negative, so this can only change sign at a point where it crosses the x-axis. In other words, at a point where this is equal to 0. So because there are no zeros, this quantity can never change sign. So it's either always positive or always negative. And to figure out which one is the case, we just plug in x equals 0, and that tells us whether the thing is positive or negative. So this only applies to the case where the discriminant is less than 0, and the graph never crosses the x-axis, and we have no real roots. Let's do two examples. You might want to try these before you look at the solutions. I'm going to work through the first one. again I follow the same steps. I bring all of the non-zero terms to one side, and I'm going to bring them over to the right hand side here. So I have x squared minus 4x plus 4 greater than or equal to 0. And I'm going to change that around just because I feel more comfortable with my greater than or equals on the right hand side there. And now you can see that the above reasoning is going to apply here. I have repeated roots. When I'm looking for two numbers, when I multiply by each other, I get 4. And when I add, I get minus 4. I'm looking at x minus 2 times x minus 2, or x minus 2 squared is greater than or equal to 0. Well, where does that happen? This is true for all real numbers x. So the solution set are given by x as an element of the real line from minus infinity to infinity, or any x an element of the reals will work. So the solution set here is the set of all real numbers. For the next one, I'm going to check the discriminant. Here we have a equals 1, b equals 1, and c equals 1. And we have the discriminant is b squared minus 4ac, which is equal to 1 minus 4, which is minus 3, which is less than 0. And so, try as I might, I cannot find real factors to this, or real solutions to x squared plus x plus 1 equals 0, because this discriminant is negative, and when I try to use the quadratic formula, I get the square root of a negative number. And so therefore this thing is irreducible. So the reasoning here applies. It's either always positive or always negative. It stays, its graph y equals x squared plus x plus 1 always has positive y values, it never crosses the x-axis, so it either always has positive y values or always has negative y values. So the values of x squared plus x plus 1 are always greater than 0 or always less than 0. How do I decide? Well, when x equals 0, x squared plus x plus 1 is 1 which is greater than 0, and therefore, since one of them is greater than 0 and it never changes sign, then all of them must be greater than 0. So therefore, x squared plus x plus 1 is greater than 0 for all real x, or for all x from minus infinity to infinity. Now my initial problem was to decide where this is less than or equal to 0. I know it can never be 0 because the discriminant is negative, and now I've figured out that it's always positive, so therefore this never happens. So x squared plus x plus 1 is less than or equal to 0. Never happens for a real number x. So the solution set to this inequality is the empty set.